Hi everyone, welcome back to the channel. If you're new here, I am Oswald and this is episode 3 of our Computer Science Mastery series. Today, we are tackling something that literally every CS student struggles with at some point: algorithms. Now I know what you're thinking: oh great, another boring lecture about sorting and searching. But here's the thing: algorithms are actually a secret weapon that separates students who barely pass from students who absolutely dominate their exams. And by the end of this episode, you're going to understand not just what algorithms are, but how to think like the top students in your class. We're going to cover everything from Cambridge and IB requirements to real-world applications, and I'm going to show you the exact mindset shift that makes algorithms click. Grab your notes, settle in, and let's get into it. Alright, let's start with a big question. What actually is an algorithm? Most textbooks will tell you it's a step-by-step procedure to solve a problem. Well, they are right. Technically, they're correct. But it's also completely useless. That definition doesn't help you understand what makes a good algorithm or how to create one yourself. Let me give you a better way to think about it. An algorithm is a decision-making machine. It's a set of instructions that takes some input, makes decisions based on that input, and produces a predictable output every single time. Let me break that down into 4 core concepts. 1. Decision making. Algorithms make choices. Should I go left? Should I go right? Is this number bigger? Is this number smaller? Have I checked every item yet? These if statements and loops aren't just syntax. They are the brain of your algorithm. 2. Patterns. Good algorithms recognize patterns. Why do we use binary search instead of linear search? Because we have recognized the pattern that sorted data can be split in half repeatedly. Pattern recognition is what separates a beginner's brute force solution from an elegant algorithm. 3. Efficiency. This one's huge. Anyone can write code that works. But can you write code that works fast? That uses minimum memory. That scales when you have 1,000,000 items instead of 10. Efficiency is what makes an algorithm professional grade. 4. Predictability. Here's something students forget. Algorithms must be predictable. Given the same input, you should get the same output every other time. No randomness, no guessing. This is why we can test algorithms and trust them to run our entire digital world. Think of it this way. If I asked you to explain how you get ready in the morning, you could give me steps. But is that an algorithm? Only if those steps involve decisions. If I'm late, skip breakfast. Patterns, I always brush teeth after breakfast. Efficiency, organize clothes at night before. Unpredictability, same routine equals same result. That's what separates a random list of instructions from a true algorithm. Now, if you're doing Cambridge IGCSE or A level, you need to know that Cambridge doesn't just want you to write code. They want you to prove you understand what's happening. And they test this in very specific ways. I'm going to walk you through the 4 big ones. 1. Trace tables. A trace table is basically a slow motion replay of your algorithm. You create columns for every variable, and row by row, you write down exactly what each variable's value is after each line of code runs. Cambridge loves this. Why? Simply because they force you to think like the computer. You can't fake your way through a trace table. Either you understand what's happening or you don't. Here's a pro tip. Practice trace tables until they feel boring. Because on exam day, when you're nervous and the question is complex, trace tables become your safety net. 2. Pseudocode. Cambridge has specific pseudocode conversions. You need to know their syntax for assignment, if statements, loops, arrays, and procedures. Don't try to write Python or Java in your exam. Write clean, Cambridge standard pseudocode. The examiners are specifically trained to mark pseudocode, and using their format makes their job easier, which means more marks for you. 3. Flowcharts. Yes. Flowcharts still matter. You need to know the difference between ovals, the start and the end, rectangles, the processes, diamonds, the decisions, parallelograms, the input or output. Cambridge will ask you to either create a flowchart from a description or interpret one and write the corresponding pseudocode. Practice converting between these representations. It's 3 marks if you know the rules. 4. Dry running. This is similar to trace tables but more informal. The examiner might ask, what's the output of this code when x is equal to 5? You need to mentally execute the algorithm and show you're working. The trick? Write it down step by step. Don't write it in your head. Show every iteration of every loop. Examiners give partial credit for method even if your final answer is wrong. 5. Time complexity basics. Cambridge introduces big O notation at A level. You need to understand O1, which is a constant time, On, which is a linear time, On squared, which is a quadratic time. You won't do complex proofs, but you should be able to look at nested loops and say, oh, this is On squared, or explain why binary search is O log of n. The bottom line is that you should master the documentation methods. Code alone isn't enough. You need to communicate your thinking clearly. Now, for those of you doing IB Diploma Computer Science, the approach is slightly different. IB is all about computational thinking. They want to see that you can think like a computer scientist, not just code like a programmer. Yes, I know. Computer science is not programmer. Yes. Here's what that means. 1. Computational thinking. This is your ability to break down complex problems using decomposition, where we break down big problems into smaller ones. Pattern recognition, where we are able to spot similarities. Abstraction, where we can easily focus on what matters and ignore the details. Algorithm design, where we're able to create step-by-step solutions. IB questions often start with a real-world scenario and ask you to identify where these skills apply. You have to practice articulating your thought process, not just writing code. 2. Decomposition and abstraction. Let's say IB gives you a problem. Design a system to manage a library. A weak student jumps straight into code. A student says, first, I'll compose this into user management, book inventory, checkout system, and late fees. Then I will abstract for now. I'll focus on the checkout algorithm and assume user authentication already works. See the difference? You are showing you can think strategically before coding. 3. Thinking recursively. IB loves recursion. You need to understand best cases and recursive cases. Of course, later on, we are going to go into detail into some of the things. 2. Trace recursive calls. 3. Compare recursive versus iterative solutions. 4. Know when recursion is appropriate. If recursion makes your brain hurt, you're not alone. But here's a secret. Draw the stack. Yes, draw the stack. Literally draw each function call, stacking up, and then resolving. Once you visualize it, recursion becomes way less mysterious. 4. Algorithm justifications. I will ask, why did you choose this algorithm? You need to justify based on 1. Time complexity. Is it fast enough? 2. Space complexity. Does it use too much memory? 3. Context. What are the constraints of this specific problem? Here's an example. I chose merge sort over bubble sort because the data has 10,000 items, making an O to n squared algorithm too slow. Merge sorts O n log of n complexity is appropriate here. That's the kind of level of thinking that IB wants to see. 5. Case study algorithm interpretation. Every year, IB publishes a case study. You will need to read and understand algorithms in the case study, explain how they work, suggest modifications or improvements, connect them to theoretical concepts. Start reading the case study early. Don't wait until exam season. The students who do well are the ones who have spent months getting comfortable with the case study content. The bottom line here is, share your thinking. IB doesn't just want right answers. They want to see that you can think computationally and justify your decisions. All right. Real talk time. I have tutored and taught hundreds of computer science students, and the same mistakes come up again and again. Let me save you some pain by calling them out now. 1. Overcomplication. Students try to write the most clever, sophisticated solution possible. They add unnecessary variables, complex conditions, and try to handle edge cases that don't exist. The fix? Start simple. Get a basic version working fast. You can optimize later. The best algorithm is the one that's correct and readable, not the one that shows off. Second struggle, not breaking down problems. You look at a question and your brain just freezes. The problem feels too big, too complex, or too overwhelming. Here's a simple fix. Ask yourself, what's the absolute first thing this algorithm needs to do? Then, what's the next thing? Build up piece by piece. Every complex algorithm is just simple steps combined. Third struggle, misunderstanding loops and conditions. I see students who use a for loop when they need while. Forget to increment counters. Of course, that will mean they will end up having infinite loops. They put conditions in the wrong order, and then they do not understand loop termination conditions. How to fix it? Stress through loops manually. Use actual numbers. If a loop is supposed to run 5 times, write out all 5 iterations with the real values. See what's actually happening. The fourth struggle, failing to think in steps. You try to solve problems the way humans think, holistically, intuitively. But trust me, computers are dumb. Yes, I said it, computers are dumb. They only do exactly what you tell them, one instruction at a time. How do you fix this? Narrate your algorithm out loud. Literally say, first, I initialize the counter to 0. Then I check if the counter is less than 10. If it is, I add the next number to my total and increment the counter. If you can't explain it in simple English, you can't code it. Okay, this is where we talk about what actually separates top students from everyone else. It's not intelligence. It's not some magical talent. It's mindset. Let me show you how top computer science students think. 1. They think in examples first. Before writing any code, they work through 2-3 concrete examples by hand. If the algorithm sorts numbers, they grab 52819 and manually sort it while noting what decisions they are making. Then they code that process. Average students try to code abstractly from the start. Top students build from concrete examples. 2. They break everything into functions. A top student will write function main, data, get input, result. See how clean that is? Each function does one thing. Easy to test, easy to debug, easy to understand. Average students write one massive block of code with everything tangled together. 3. They visualize like a CPU. When debugging or designing, top students literally imagine buying the computer. They step through code line by line, tracking variable values in their head or on paper. They see the flow of control. You can practice this. Take any piece of code and draw a box for each variable. As you trace through, update those boxes. You are training your brain to think like a CPU. 4. They do not panic in coding questions. Here's what top students do when they see a hard coding question. 1. They read it twice slowly. They identify inputs and outputs. They walk through an example by hand, identify the pattern or logic needed, pseudocode the structure, and then fill in the details. Notice coding is step 6, not step 1. Average students panic and start typing immediately, hoping the answer magically appears. That will never work. That never works. 5. They test constantly. After writing every 3 or 4 lines of code, top student test. They don't write 50 lines and then wonder why nothing works. They build and verify incrementally. Think of it like building with Lego. You don't build an entire castle and then check if the foundation is stable. You check after every layer. Now, let's talk about why this actually matters. Algorithms aren't just examples or then just exam questions. They literally run the world. Let me give you 4 massive examples. 1. Pathfinding. Every time you use Google Maps, Uber, or any GPS system, you are using pathfinding algorithms. The most common one is Dijkstra's algorithm or ESTA. These algorithms calculate the shortest route through millions of possible paths in seconds. That's not magic. That's a well-designed algorithm making smart decisions about which paths to explore. 2. Sorting and searching. Every database query, every Google search, every time you organize your photo library, sorting and searching algorithms are working behind the scenes. Imagine if Google used bubble sort or n squared instead of optimized algorithms. Searches would take minutes instead of milliseconds. The entire internet would be unusable. 3. Encryption. Every secure website, every password, every credit card transaction uses encryption algorithms. RSA, AES, SHA. These are the algorithms that protect your data. Understanding how these algorithms make decisions about encoding and decoding data is fundamental to cybersecurity. 4. AI decision trees. How does Netflix recommend you shows? How does Amazon know that you might buy? How do self-driving cars decide when to brake? Decision tree algorithms. They take input data, follow branches based on conditions, and make predictions. Machine learning is, at its core, algorithms learning to make better decisions based on data. What am I trying to say? When you learn algorithms, you're not just preparing for exams. You're learning the fundamental building blocks of every technology you use on a daily basis. Alright, I want to end this with something important. If you've struggled with algorithms, if you've ever felt like you are just not a CS person, I need to hear this. Algorithms aren't about being smart. They're about training your thinking. Just like you can train your body to run faster or lift heavier, you can train your brain to think algorithmically. Every single top CS student was once a beginner who struggled. Every single one had moments where loops didn't make sense or recursion felt impossible. The difference is key. They kept practicing. Here's my simple small challenge to you. Small daily habits. Spend 15 minutes a day. Try through an algorithm. Solve one simple coding problem. Convert pseudocode to a flowchart. Explain one algorithm aloud to yourself. That's it. 15 minutes. No marathon study sessions, no cramming, just consistent daily practice. Because here's the truth. Your brain physically changes when you practice algorithms. Neural pathways strengthen. Pattern recognition improves. Logical thinking becomes more natural. You are not behind. You are not struggling because you are not smart enough. You just haven't trained enough yet. And the beautiful thing, once algorithmic thinking clicks, it stays with you forever. It's like learning to ride a bike. You might get rusty, but you never truly forget. So don't give up. Don't tell yourself you are bad at algorithms. Instead, commit to the daily practice. Commit to thinking in steps. Commit to breaking problems down. You've got this. All right, everyone. That's episode 3. We covered what algorithms really are, the IB and Cambridge specific requirements, common struggles and how to overcome them, the mindset of top students, real-world applications, and why you absolutely can master this. If this helped you, smash that like button and subscribe so you don't miss episode 4, where we're going to dive deep into data structures. Drop a comment below. What's your biggest algorithm struggle? What clicked for you in this episode? I read every comment, and your questions help me make better content for you. Until next time, keep coding, keep practicing, and remember, think in steps. See you in the next one.